Hello guys, and let us start with the numerical of one-way slab. Design a slab over a room of 2.5 into 5.5 meter to carry an imposed load of 5 kN per meter square and a floor finish of 1 kN per meter square using M20 and Tutor steel. So starting with the solution, we have been provided as FCK, that is characteristic strength of concrete, 20 Newton per mm square. Fy, yield strength of steel, 415 Newton per mm square, that is Tutor steel. Now continuing to the Lx, okay, along the x-axis 2.5 meter, we'll consider the shorter side as x, Ly as 5.5 meter. Means be clear, this is just a clear span, okay, without any this is not an effective length, just a simple length along the x-axis and y-axis. Now for the depth, step 1, that is taking L by D ratio. So we are not considering, or we are not provided with any cases, that is either it is simply supported or continuous. So what I will do is I will just consider this as a simply supported. So I will take the ratio of L by D as 25. So L by D as 25, assuming simply supported case, simply supported slab. Okay, now D is equal to 2.5, that is the length, divided by 25. This comes as 0.1 meter. Now taking a greater value, so almost 0.11, so that comes as 110 mm. Okay, adopting 110 mm thickness of slab. And from the table 16, okay, we have this for the nominal cover, that is the effective depth. Okay, make sure that is the effective depth. Now we have to calculate the overall depth. So effective depth plus the considering the bar size of 10 mm. Okay, it is up to you whichever size you can take. So I'm taking 10 mm, and for reinforcement up to 12 mm we can deduct the nominal cover by 5. So considering the mild exposure we get 20, and subtracting 5 we get 15 mm, clear cover as 15 mm. Now total depth, that is the overall depth, is equal to effective depth plus half bar size, because we have to consider the half bar size, plus clear cover. So now this comes as 110 plus 10 by 2 plus 15. So finally we get as 130 mm as the overall depth, okay, including the cover of the concrete. Now let us draw the section. So these are the bars that I place. Okay, let me make you clear about the total depth. Okay, so this is the effective depth considering the half of the bar size, and this is the clear cover, okay, excluding the bar size and the half bar size, that is half by 2, sorry, bar size by 2. So now as a whole you can understand the concept of total depth. Now second step is to find the effective span along both axes. So along x-axis, from the chord, okay, we have already done in the beam also, from clause 22.2 we will take the smaller value of two calculated value. One is clear center to center length. Okay, the effective span of a member that is not built integrally shall be taken as a clear span plus the effect, or the effective depth plus the bar size. Okay, so center to center distance 2.5 plus 0.23 plus 0.23 by 2. 0.23 is the bearing width, that is the slab rest on the half of the beam, or with the support we can say. So this comes as 2.73 meter. And the second case we consider here is the clear span plus effective depth. So this comes as 2.5 plus 0.11. okay, we have calculated the depth, so this comes at 2.61 meter. As I said, we will be taking as a smaller value of these two, so taking less value, hence effective length along x-axis is 2.61 meter. Along y-axis the same thing. Okay, one is center to center distance, another is clear span plus effective depth. So center to center distance 5.5 plus bearing width 0.23 by 2 plus, okay, into 2 we can directly do it. So this comes as 5.23 meter. Okay, and clear span plus effective depth. So this comes as 5.5 plus 0.10. So this will not be 0.11. Okay, I'll make it clear. The 5.6 meter. So why it is like this? Because basically, okay, x-axis is a shorter span as we have considered. So reinforcement will be provided in only on the shorter side, that is parallel to the shorter side. So not in the longer side. Hence the reinforcement responsible for taking the deflection is provided along the x-axis only. Hence we do not consider in the y-axis. Okay, we have reduced the bar size because 110 mm is the effective depth including the bar size. Now if I don't include the bar size, then it will be 100 mm. Now third step is to calculate the load acting on the slab. Imposed load is equal to 5 into 1, that is the considering a 1 meter span, okay, as in the beam. Floor finish 1 into 1 kilonewton per meter square into 1 meter. Okay, so as I have already said, so we are considering a unit length of slab. Okay, so just considering a unit length of slab as a beam of width 1 meter. Okay, beam section of width 1 meter. So we'll consider like that. Self weight is a concrete, so gamma c, that is the self unit weight of concrete, into B into D, that is the dimension, so as in the beam. So this is taken as 3.25 into 1 into 0.130. So this comes as 3.25 kilonewton per meter. Sorry, that is 25. Okay, so this comes as 3.25 kilonewton per meter. Total load 9.25 kilonewton per meter. Factored load, just taking a partial factor of safety as 1.5, so this comes as 13.875 kilonewton meter per meter. Now calculating the moment, okay, from the load. For UDL it is mx is equal to WL square by 8, 13.875, that is the total load, factored load, into length along the shorter side always, because the load is acting in the shorter side for the one way slab. Okay, so this comes as 11.214 kilonewton meter. Now for the shear, V max is equal to WL by 2, obviously LX, 13.875 into 2.61 divided by 2, this comes as 18.1 kilonewton. Moving on to the next step, that is the check of depth, whether the depth of the slab is sufficient to carry this moment. So for FE 415, mx is equal to 0.138 BD square FCK. Substitute the value of moment 11.214, 0.13 into converting into Newton meter. Okay, so this comes as Newton mm. 0.138, B is 1000 mm, D square. So we are checking. Okay, so just put as D square into FCK, that is 20. Now calculating this value on solving, we get the depth required as 65.42 mm. So we have provided 110. Okay, so which is less than D calculated, hence the depth assumed is okay, or the depth taken is okay, 110 is safe. Step 6 is to find the area of steel required. Okay, from page 96 annex G, considering under reinforced section, you can see here just take this formula. So m is equal to 0.87 Fy AST d 1 minus Fy AST by b FCK b into d. So we are interested to find the value of AST and substituting other terms as 11.214 into 10 to the power 6, converting into Newton mm. 0.87 Fy 415, AST is unknown, d is taken as 110 mm, so 0.11 into 1 minus, so sorry, converting into mm, 110, 1 minus Fy, that is 415, AST is unknown, FCK as 20 and B as 1000, D as 110. We get this value of AST on solving as 316.34 mm square. So this is per meter, okay, make sure that. Check for AST, whether the area of steel provided is sufficient or not. So from code we have the minimum area of steel is to be taken as 12% of, sorry, 0.12% of BD, the gross area. Clause 26.5.2.1 page 48. So 0.12 by 100 into B as 1000, D as 130 or overall depth. So as I said, gross area. This comes as 156 mm square, which is less than the area of steel provided. Spacing now. The spacing between the main reinforcement bars, okay. So let us assume this is the bar within the 1000 mm, okay. AST individual 1000, that is this overall width we are considering, AST provided and AST of individual. In this way we can find the spacing. 1000 by area of steel provided 316.34 divided by 78.58. So considering a bar of 10 mm, we get the area of that bar as 78.58. So the spacing between these two comes as 248.24 mm. So considering phi as 10 mm, area comes as pi by 4 into 10 square, so 78.58 mm square. So the spacing between the bars should be at least 248.24 mm according to the area of steel provided, okay. Now let us check whether this is sufficient or not with the codal provision. So the code says at least 300 mm or 3 into D, that is 3 into 110 effective depth, okay. So this comes at 330 mm. So the value of spacing is less than that of the codal provision. So this comes as okay. Now providing 10 mm dia bars at 200 mm. So the spacing, the lesser the spacing, the stronger the structure is. So we are providing 200 mm, but make sure it should not be much more closer, because we the workability of the labor becomes difficult. Check for shear. Vmax is equal to 18.1 kilonewton. Tau max is equal to Vmax by B into D, that is area. 18.1 into 10 to the power 3 Newton divided by 1000 into 110. This comes at 0.164 Newton per mm square. Now let us check with the value, with the codal provision, whether it is suitable or not. Now check for shear. AST B by D percentage 392.65 by 1000 into 110 into 100 percentage. Now this comes at 0.356%. From table 19, AST by BD percentage, and we will calculate the stress, shear stress, okay, for M20 concrete, and the value we have lies between, or the value calculated lies between 0.25 and 0.5, okay. So we will be interpolating value between these two, that is 0.25 and 0.5. 0.3 is 56 and 0.50. Now let us find the corresponding value, 0.36 and 0.48. Now interpolating by linear interpolation, we get this at 0.41 Newton per mm square. That is design shear strength or shear capacity is equal to K into tau C. Now K is a constant which is taken as 1.3 into 0.41, 0.534 Newton per mm square. So the value of K is taken from the code, okay. Tau permissible. Tau permissible is greater than the tau max we have calculated. So it is okay. It is safe in shear. Now checking for deflection. L by D is equal to 2.61 by taking the smaller dimension, okay, 0.11. This comes as 23.72, and also alpha is equal to 20, beta is equal to 1. I'll make you clear about these values. Lambda is equal to 1, delta is equal to 1. So for gamma, okay, it is to be calculated from AST by BD 392.63, B is 1000, and overall depth is 130, 100%. So this comes as 0.302%. And for FS, 0.58 into FY, this is from code, okay. AST required by AST provided. We get this value 0.58 into 415 into 316.343 provided is 392.68. This comes as 193.92 Newton per mm square. So the value of alpha, beta, lambda, gamma, delta are all taken as the codal provision, okay. Page 34, figure 4 from IS 456. You can see here. So the value of all these terms, as I said, for simply supported is taken as 20 for alpha, okay. For a span above 10 meter, the value of alpha may be multiplied by 10 by span, but the value is not greater than 10 meter, is just 2.1 meter. So we are taking beta as 1. Similarly, the value of lambda is taken as 1, delta is taken 1, because there is no compressive reinforcement in slab. So in that cases, the value are taken as 1. The main term here we consider is gamma, okay. So you can also understand from this graph. So Fs is calculated. Percentage of Fs we have 190 something. According to that, we will take the modification factor, okay. So if we see here, it lies between the 190 and 200. So this value comes as 1.8. Then alpha, beta, gamma, lambda, delta is equal to 20 into 1 into 1.8 into 1 into 1. So this comes as 36. And also for the deflection criteria, the value of L by D should be less than alpha, beta, gamma, lambda, delta. So it is okay because we have L by D as 23.72. Step 9, that is development length. So development length is also taken from the codal provision from page 42. LD is equal to 5 lambda by 4 into tau D. LD is equal to 5 lambda S by 4 into tau BD. Now substitute the value of this term. Phi is the bar size, okay, which is 10. We can understand this term. Phi as stress, tau BD design bone stress, and on the basis of the concrete grade, the value of tau BD is taken, and for the deformed bar, the value may be increased by 60%. So on that basis, taking phi as 10, sigma s as 0.87 into 415, 87% of the yield strength, 4 into 1.2, because the bar size can be multiplied by 1.2, and increase of 60% in the tau BD. Okay, so tau BD we have already calculated previously, that the value has to be substituted. This comes as 470.11 mm. For checking whether the development length is sufficient or not, ml is equal to 0.87 fy ast d 1 minus ast fy by fck bd. This is the from codal provision. Okay, let me show you. Okay, ml is the moment of resistance of the section, so the value should be less than that of this. And f, as I said, 0.87. So substitute the value of 0 of all these terms. We will calculate the moment. Fy 415 into ast, taking as a half. Okay, 392.6 divided by 2 into d, that is 110. 1 minus ast, that is taking as a half. Fy 415 by b into d, that is 20 into 1000 into 110. The half of the area of steel is taken because at the ends where the development length is to be provided, only half of the bar reaches. Okay, other bar are ended at the mid portion. Only half of the bar reaches to the other end. Now this comes as 7.50 kilonewton meter and 1.3 ml from the code, as I said, ml by v, 1.3 into 7.5 into 10 to the power 6, converting to newton mm, v as 18.06 into 10 to the power 3 newton. So this comes as 538.49 mm, which is greater than development length. Okay, so value of ml by v in the above expression may be increased by 30%. Here LD is less than 1.3 mlv, so there is no necessary of addition of the anchorage length L naught. Okay, so L naught can be taken as 0. For distribution bars, the main reinforcement has been already discussed. Now for reinforcement of the distribution bars, AST minimum as 156 mm square, taking the AST minimum 156 by 78.33. Now this comes at 503.39 mm, which is less than or equal to 450 mm should be taken. Okay, 5 into D, which is less than 550 mm. So okay, providing 10 mm bars at 300 mm center to center.